Alright, let's consider this question. Is f differentiable on the given interval? Okay. First of all, let's look at the derivative of this. And before I can do the derivative of it using the power rule, I'd like to rewrite this so that it's in a little bit more friendly notation. So how could I rewrite that? X to the 1/3 power. So what is our derivative of this? 1/3 x to the 1/3 minus 1, which is negative 2/3 power, right? Or if I saw this, it would be 1/3 x to the 2/3 power. Okay? Or I can also have that in radical notation as well. But what about the domain of this? Where's this not differentiable? 0, right? If there's a 0 down here, then it's not differentiable. What about 0? So we're going to look at x equals 0. It's not differentiable, and it's that interval right there includes 0, right? So the question is f differentiable on the given interval? What do you say? No. Good. Let's say no, because not differentiable at x equals 0. Well, what about the interval from -2 to -1? Yes, because the first derivative exists for every number in this particular interval. So let's write that. We'll say yes, because the first derivative exists, it's differentiable for every number in the interval -2 to -1. Okay, we're going to sidetrack just for a second, and before we move on to the next example we're going to work, let's just look at this idea and get a grasp of the derivative of a function. So if we're given a graph, this is going to be an x squared graph. Using our power rule, what would be the derivative of this? 2x, right, which is a linear function. So if I had to match it down here, which one of those would possibly match? Not directly, but not the exact derivative, but just your x function right here. Okay, what about a cubic? The derivative of this would be 3x squared, so basically an x squared function. So the derivative of that one would be here. Cosine of x, you haven't done this yet. We're going to talk about this later, but it's negative sine of x, so that would be paired with this one. And then if you have an x to the 4th function, what's the derivative using power rule? 4x to the 3rd, so basically it's a cubic function of some sort. So we can see this is just a little bit of a visual for functions and what the derivatives of their functions look like. And basically it's 1 degree less, except for our trig functions, which we'll talk about those specifically later. Also, let's make some notes here. To be differential at a point, the derivative from the left and the derivative from the right must be equal at that point. Basically, it's continuous there. If the one-sided limits are not equal at the point, then the derivative does not exist at that particular point. You cannot find the derivative, and here's what we want to pay attention to, where you have a sharp point or corner, because the derivative from the left and the right will not be the same. So here's our definition of derivative, and we've been talking, it's a little bit different notation, but similar. Let me move these out the way now. Okay, the derivative from the left of c equals the derivative from the right of c, therefore the function has a derivative at the point c. Okay, here, this is a special function. This is actually explained in your text. It's the absolute value of x function. If you look at the derivative from the left of c, we found the slope of the tangent line there to be -1. Coming from the right, it was positive 1, so the derivative from the left is negative 1, the derivative from the right is positive 1, therefore the derivative does not exist at C. An example of a cusp or a sharp curve right here, so no derivative at a sharp point or a corner. So it says find the point in which the function is differentiable. So it's differentiable everywhere but here and here. Interval notation to explain that is negative infinity to 1, union negative 1 to 1, union 1 to infinity. Actually not union, those are particular points only. Alright, and then here, negative 2 is not included because, so it's not a bracket 2, because can you find the left hand of that? No, it's not there. You remember the left and the right. So because you can't see it from the left, then not. Also, your textbook, and you may need a few minutes to jot this down, the definition of a function, it has a vertical tangent line at x equal a at the point P f of a if f is continuous at a and if the limit of the derivative, the limit of the absolute value of f prime of x as x approaches a equals infinity. And then we'll also have the definition down here of when we have a cusp, and that says if the first derivative approaches infinity as x approaches it from one side, and then you get negative infinity as it approaches from the other side. So I'll give you a few minutes to write these definitions down. And just some examples of cusp saying, so here, if you took the limit, you have a vertical asymptote here. Okay, so that would be at P. Here you can see where it's, if you was looking at it from the left, it'd be approaching positive infinity, but if you look at it from the left, it would have negative infinity, so you would have a cusp there, and also at this particular case here. Okay, so let's look at an example. Determine whether f has a vertical tangent at the point 0, 0, or if it has a cusp at 0, 0. So we're given the function f of x equals x to the 5th, x raised to the 5/3 power. And we come back over here and we recall that to determine if it's a vertical tangent, then we would have this scenario. So we need to take the limit of our f prime of x as x approaches a and see what we get. If we get infinity, then we know we have a tangent line. If we don't, then we would say no. So let's do that. First thing we need to do is find the derivative. So f prime of x is going to be what? 5/3 x to the 5/3 minus 1, which is going to be x to the 2/3 power. Okay, so that's going to be that. Now we look in where we want to take the limit of f prime of x as x approaches a, which in this case is 0, as x approaches 0. Okay, that's our x value, so if we plug that in, so this is x approaches a in our definition, we'll plug in all the information in the next one. So let's just have a paper trail. Limit, what is our f prime of x? 5/3 x to the 2/3, and x is approaching a. What's our x value? That's given 0, so now let's use substitution in there. What happens if you get a 0 there? You're just going to get just equal to 0. Well, does that equal infinity? Yeah, so by the definition, do we have a vertical tangent line here? No, so we say since that is not equal to infinity, no vertical tangent at 0, 0, at the point 0, 0. Okay, that was for part A. Alright, for part B, we want to look at the cusp situation. So we come back over here, remind ourselves. So we want to look at the first derivative as x approaches infinity. So we want to look at it as it approaches it from one side, and then also as it approaches it from the other side. And if we get one to be positive and one to be negative, then we know that we'll have a cusp. But in our particular case, when we look at our derivative, what about f prime? It's always what? It's always positive or always non-negative. So there's not going to be a place in which there's a cusp form. So for B, we can just look at that and say since f prime of x is always non-negative, no cusp is formed. Okay, just quickly to walk you through this base case of what we've shown in the handout, use the right hand and left hand derivatives to prove that f is not differentiable at a. So we have the absolute value of x, we have our limit definition here. We evaluate that at 0 from the right. So first of all, plug 0 plus h into this function and allow x to be 0. Simplifies here. And when we test this as a right-hand limit, you get h over h, which is just 1, but it's 0 to the right, so it's positive 1. When we test it from the left, we get negative 1. Therefore, the left-hand and right-hand limits do not agree, so the f prime of 0 does not exist, and it's not differentiable at that point.